Well, hello everyone, and welcome back to Adrian's Digital Basement 2. This is a quick follow-up video to the PCXT troubleshooting video, which I had just posted on the second channel. If you haven't already seen that video, I recommend you go watch that first, because I'm going to be talking about stuff from that video in this one that won't really make sense unless you've already watched it. So I was going to start off with one thing. This is my XT IDE card, the one you saw me put in backwards in this motherboard in the last video. Well, I think I mentioned in the video that all that was damaged was the ROM chip on here, so I've replaced that and I've been using this card without any issue. But I've gone ahead and put labels on here towards front, towards back, and I did it on both sides of the board. That way I can try to avoid doing this again. There was a comment on the video here from Necroware, and if you haven't seen his channel, I highly recommend it. He does lots of repairs on PC motherboards and stuff like that. And he mentions that he did the same thing just recently on his XT IDE and actually ended up with a little bit more damage, like the 573 was damaged from getting 12 volts. Luckily, that didn't happen to me. So after reading through a bunch of really constructive and useful comments on this last video, I decided to break this out this morning and start doing some troubleshooting. Now, let me pop out this floppy card here. Now, right here in this section is where the battery damage occurred to this board. Well, at least the battery leaked on this. There was a multi-IO RAM board here with a clock on it, and it kind of corroded some of the traces here. So I decided to really start poking around and looking for any damage. Most of the damage happened under this IC right here, and I actually removed it from the board, and it's in a socket right now because I wanted to check underneath it just to ensure that none of the traces were damaged. And you can't really see what's going on underneath there, right? Because the traces run this way along the board. So I took it out just to check it out. There's a trace right here which looks like it's kind of eaten up, and it goes under the chip, and that's the one I was specifically looking to figure out. But after removing this and really going over everything very carefully also around this area, I found no traces that were bad. There are little spots of corrosion, you can just sort of see the little marks and stuff, but that is just the solder mask coming off the copper, and everything is actually working perfectly in this area. While I had this chip out, of course, I stuck it in the Retro Chip Tester Pro, and it did test okay. Now what we're looking at right here is the technical reference for the IBM 5160, that's the PCXT, and it seems that this clone motherboard was basically a direct copy of the original XT motherboard. I can't really find any difference on this versus on the schematics. The main difference is all the IC designators are different on this, but when I find one particular chip that does some certain function and I check all of its connections, I see that on the schematics it totally matches. So the first thing I want to check is that the IRQ and the DMA lines from the ISA bus were actually making it through to the interrupt controller and the DMA controller. I didn't try that in the original video. So I broke out my little proto board here, which luckily has a header here that's labeled with all of the signals, and plugged that into a slot, and then I did confirm that the IRQ and the DMA channel signals are making their way over to these two chips. The floppy controller uses IRQ 6, and I think it uses DMA channel 2, although I can't remember if I'm correct on that. Sorry if I'm wrong, but I had looked that up, and I think those were the ones it was using. DMA has two signals. There's a request signal and then an acknowledge signal, and both of those were making their way here, and the IRQ is making its way here. I also checked, just in case there was any issues in the slots, is that the IRQ and the DMA signals make their way from this side of the board to this side of the board. So there are no breaks in the middle here, because if I recall, one of these slots was a little bit corroded as well on the original board, but I cleaned that up with some, I think it was vinegar or something like that. So at this point, all of the traces seem fine. All of the IRQ and DMA signals were getting through to the controllers. I couldn't really find any damage from the battery leakage. Now, there's a couple other things I want to mention that were in the comments. One is that the PC absolutely needs the DMA controller to work at all. And that's because I think it's DMA channel 0 is used to refresh all the DRAM on the board. Now, when we talk about refresh, when you have DRAM chips like this, not static RAM, but DRAM, if you don't continually access every location of memory, or not quite every location, but every row or column or something like that, the data that's in the DRAM fades away because they're just little capacitors in here. So you have to keep refreshing it. And the PC architecture uses the DMA controller to do that. So if you pull out the DMA controller, obviously it's not going to be able to refresh the memory anymore, and it's not going to boot. In addition, IRQ, I think it's 0, is like a timer, and it's required also for the BIOS to work properly. So taking out the interrupt controller will also result in a non-working system. So the reason why I bring that up is people also pointed out correctly that if these are not working, of course you're not going to have a working system. And this system, as we saw, does pretty much work. With the XT IDE in there, when I didn't plug it in backwards, boots up the system without any issue, and it's fully operational. All 640K, it runs normally. It's probably worth me just briefly talking about what DMA actually is. It stands for Direct Memory Access. Normally the CPU, which is right here on this motherboard, is what controls the address bus that goes to all the various components on the board. And that's because if the CPU wants to talk to a specific location in memory, like in RAM or ROM or one of the cards, it sets up the address bus and then it reads or writes data from that device over the data bus. Well, when you have direct memory access, what that allows something to do, like say a floppy controller card, is actually take control of the address bus itself, and it doesn't rely on the CPU anymore to generate those address lines. It's actually doing it directly. The reason that can be advantageous is something like the floppy controller can actually copy information it reads off a disk and stick it directly into RAM, and it doesn't even require the CPU to do the handling of the data bus. Normally the CPU would have to read a byte from the controller and then it would have to write it to the RAM. It uses internal registers for that. There's a whole lot of extra cycles going on just to do that. If the floppy controller, well, it's not in the machine, but if the floppy controller here could just copy information directly into the RAM bypassing the CPU, you can get a lot better throughput on the system. Sound cards are a good use case for the DMA channels, like a Sound Blaster card, because it also allows much faster transfer of information from the RAM into the sound card without relying on the CPU to be moving or pushing that data around. If we look here at the schematics for the XT, this is the DMA controller chip right here. There are 3 ICs here, an LS244, an LS670, and a 373 that generate address lines 0. So there's 0 through 7, we have 8 through 15, and then we have 16 through 19. That's the 1 megabyte of address space on the 8088 architecture like this. So these chips, I think, are generating those signals so that when things need to do DMA transfers or whatever, the CPU is no longer generating those address lines, but the DMA controller through these ICs are. So we know that this is the DMA controller here that I socketed. Well, wouldn't you know it that the other ICs that are on that schematic I just showed are this one, the 670, this one, the 373, and this one right here, the 244. And notice the battery leakage that we had on this machine was right in this area right here. So potentially that really does point to a possible issue with the DMA. We established in the last video that floppy controller access does need DMA and IRQ to be working properly, but it is kind of strange that DMA clearly works because the DRAM refresh is working, and of course there's 640K. You need all of these address lines working to refresh the 640K, because A19 here, which is the top address line, is basically splitting the 1 meg address space into 512K chunks. So if the first 512K doesn't rely on A19, that just can be 0, but anything above the 512K boundary needs that to be 1. So while I was inspecting this part of the board for trace damage, something really interesting happened. I had been sanding down the traces a little bit with a fiberglass pen, and I was cleaning it up with alcohol when I noticed that this IC right here looked like it was remarked. Now I have a picture of the motherboard here before I did that cleaning, and here's the IC, YRS74LS373, so that's a latch. I'm not super familiar with what YRS is. Is that Radio Shack perhaps? But either way, like I said, I was cleaning up with alcohol and that marking started to come off. And what you see right here in the board is that same exact chip when I just rubbed it with some alcohol and the paint all came off, and underneath we have a 74LS373 from Motorola. So who knew that rebadging was going on back when this motherboard was made, which looks like it's around 1986. So I have to say that kind of made me question how reliable this IC is if it had been a rebadge? Like, what if this Motorola part was sort of like a reject, and then they just repainted the markings on it with a different label, stuck it in the board, and you know, it worked, but perhaps it's marginal. So it gave me pause as to wondering like what happened there exactly, but I didn't really think too much about it at the time. But then as I was reading through the comments, I came across this one from Ollie Wright, and he said, and I don't know what happened with the text there, that's the way it actually looks in the YouTube Creator Studio, but I had a very similar issue on a 5150. In my case, the problem turned out to be with the 74LS logic chip around the DMA controller, specifically the address latch LS373 in U18 was bad. So data from the floppy controller would end up at the wrong address in memory. Very interesting, isn't it? So again, here it is. This is the address latch. The marking is different. It's U11 on the XT. But that is definitely this IC here, and it is the latch that handles the addressing of the DMA. So with Ollie's comment that he had this exact issue, and the fact that this was like a rebadged chip, and it had been dripped on by the battery, I obviously socketed it and pulled it out of the board. So here we are with the Retro Chip Tester Pro. Let's pop in this rebadged chip I took off the motherboard in and test it. Look at that, it works. So it might be a rebadged part, it might have had some drippings on it, but it still seems to work in the tester. But just for fun, I went and grabbed another chip. Here we have a TI LS373, something I pulled out of another board. Let's pop that in here. Plug in the floppy controller. I have the VGA card connected to the capture device. I have the floppy drive connected with that same, I think, DOS 3.1 that I had in here while we were testing in the last video. And let's turn this machine on. All right, we got error number 4 still, but I'm gonna push F1 on the keyboard. And that's it. The machine's freaking booting. Now I have to say that I already tried this before I had the camera out, so I'm not like my awesome shocked self, but I was like, wow, Ollie was right, and that chip was bad. And there it is, like we have a DOS 3.3, and we do DIR, and it's accessing the floppy drive perfectly. But you know what? I've done a lot of manipulation of this board, right? I've like, you know, clean traces and took out this other IC and put that back in. Maybe it got fixed because of something else. Maybe one of the traces was like slightly marginal, me poking around caused an issue. So here, the original rebadged chip is back in. Let's turn the power on. All right, we have PC Turbo error number 4, and I hit F1. It does one click on the disk drive and it stops. So this problem is completely back. That chip is definitely the culprit, and this replacement one fixes this computer. So let's break out the oscilloscope, and here's the schematic here for that chip. And let's take a look at the signals we see on here. And incidentally, right here on the motherboard is another one of those YRS 74LS373s. In fact, there's another one there as well. Do I see any others? No, I just see those two. You know what, before we test, I'm gonna turn the power off. Let's just see if I can scrape the markings off these as well. Now I'll say that I did not have to use acetone on the other one to get the marking off. Oh, there we go, look, it's coming off. Wow, the other one came off much easier though. But this one is also coming off. And who makes this part? Motorola as well. So there it is, 74LS373N. It's just like the other one. And let's do this one here. And there we go, right before our eyes. 2 more rebadged chips. That's also Motorola 1984 part. And this one's Motorola 1984 part as well. They look like different series though. The markings on those two are different than each other. Honestly, that is fascinating that we have rebadged chips on something from the 80s. Why? Okay, anyways, back to testing here. So let's just make sure I have a good signal, and I do. That's 5 volts. Okay, so let's start probing around on these signals. Let's look at the output here. So there's pin 19. So if we turn the computer off and on, okay. So what we're going to be seeing initially are just normal address bus activity. So it's probably sitting there with error number 4, and I have to hit F1 to have it boot. All right, well, we saw it there for a second. I think this was actually driving the bus. Okay, so I've moved to pin 1, which is the enable pin on here, and we can see there's a low pulse there. And if I power cycle this thing, I think that low pulse is going to be happening all the time. And I think that has to do with the DRAM refresh. Basically, this thing is being used to generate address signals for the DRAM. Let's see how often those lows happen. All right, so there's one of the cursors. Now if I move this, can I drag? All right, well, I'm going to put this, okay. Since I can't see where I'm dragging, I just have to look at the top. So there, I think, is the other one. Let's move over here, get that onto there. Oh, I was pretty close. All right, so basically to there. On this cursor, we want it to be there. And there we go, here's the delta. It's refreshing every 3.8 milliseconds. Not sure if that's enough time for the DRAM, but anyways, that's almost certainly what these pulses are. And it's only when the LS373 is turned on that it's actually generating any of the output here. Otherwise, the signals we look at on these pins on the right are just the normal address bus being generated by the CPU. I have a hunch that the problem that's going on this chip is that probably some of the output drivers are weak. And what's happening is when it's trying to drive the DMA channel for the floppy, it's setting up these address lines, and some of them are probably not strong enough and are just being interpreted by various components on the system as a 0, even though it's probably trying to drive a 1. The best I can do right now is connect one channel of the oscilloscope to the enable pin, which on here is the red trace, and that's what I'm triggering off. And then this right here is the output pin on the chip. So this activity you see here when it's not enabled is just the regular address bus being driven by the CPU. But then see this little droopy signal right here? Let's zoom in a little bit. This little droop right here is probably going to be interpreted as a high. I hit the single shot, and notice there it's generating a low, low, low. Let's look for any highs. Well, it definitely seems like this chip is able to drive the address bus low at least. I don't know if the address bus has a pull-up resistor on it or what, but I'm going to say that that output looks fine. And the reason why it's changing right now, and the computer's not trying to access the disk drive, it's just sitting here doing nothing, is because this is the address refresh for the DRAM happening. So it's going to be constantly changing. And I am currently connected to pin 2, which is address line 8. Okay, and I've moved over to pin 5, which is address line 9. And that one looks okay. It's able to at least drive the bus low. Let's see if we can try to find a high here. Seems to be always low, never any highs. Okay, let's go to pin 6, address line 10. Okay, there it is. Oh, definitely you see some highs in there. Let's single. So there's a high. All right, here we are on pin 9. That's a little weird. I've gone back to pin 6 here. So it had a little bit of that similar little spike there. There it is. Seems like as it's going low, there's a little bit of a spike. That's probably fine. There's like some hold off time that's probably built in to the system. But going to pin 9, there it is. There's that little funky hold off time. So anyways, this high or low is being driven by this latch chip itself. All right, I'm on pin 12, which is address line 12. And I'm gonna say that looks generally fine as well. And here we are on address line 15. And we're seeing things that look okay. Okay, and then we're on pin 16 here, which is address line 14. I mean, that signal looks fine. And then finally here's pin 19. Okay, and I gotta say that that looks wrong. Like it goes high for a second and then it's just low the rest of the time. So it's almost like it's not holding that signal for the entire length. It should be holding it for the entire length that this chip is enabled, other than a little glitch or spike at the beginning, which is normal. But that actually looks wrong, everyone. Oops, let me zoom in more. There it is. That looks like a problem to me right there. And we are on right here, pin 19, address line 15. Okay, well, let's swap out to this other chip here and I'll reconnect in the same way. All right, we power it on. There is the enable signal. And we go right to 19. We're getting proper highs out of it. So notice on the other chip, we'd see a little glitch and then it would always be low. And now on the same exact address line 19, we are getting it staying near the top for the entire duration. Yep, do you see there? There's some highs mixed in there and the computer's booting off the disk drive. Also the enable signal gets a bit longer, but look at that, normal highs. Okay, I'm gonna swap back to the other chip and we'll just double check, triple check actually, that we're definitely seeing that signal as wrong. Okay, original chip back in, power this up. Let's look for any kind of high activity other than that initial glitch, because I don't think we're gonna see it. I think there's something wrong on this output pin. Okay, it's just low, 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 hit F1. Nope, do you see that? It was very, very brief, but the little glitch here got longer and then it still went low. So it's this output pin, this is the problem. It is not driving the bus high properly when it should. Unfreaking believable. And it's funny that this chip tests perfect in the Retro Chip Tester Pro, probably because maybe the output driver, like I said, is weak. So it tries to drive the bus high and then it runs out of oomph, you know, to push that 5 volts through the entire motherboard. And then it just drops back down to 0. While the other outputs on this chip do not have that problem. Oh, there it is. That's it, right there. That's it. It's crapping out. This should stay for the entire width of that enable signal. Right there. Smoking gun, right there, single. That's it. Well, it's nice to be able to figure stuff out. You know, if I had been poking around with the logic analyzer or the scope without knowing that that was a bad chip, to find this, well, it certainly would have taken quite a bit of time, because I'd have to know that A, this was a DMA problem specifically, and I mean the comments were pointing that direction. So I was kind of thinking that that was the case. But you have to think about that you have to set up the oscilloscope in this exact way and then know that while this chip is enabled, that the highs should go the entire width of the enable, and it's not. So anyways, so that's it, everyone. This board is fixed, I guess. I mean, it was certainly a very fun troubleshooting exercise. So I'm gonna grab a marker and we are going to X out this crappy rebadged chip. And I'm gonna pop in the correct one. And there it is in the board. So this board is repaired. I still don't, I wonder what the error 4 is that happens at boot. That's probably, maybe I have it set for CGA and it's currently with a VGA card in here. I think I was doing my troubleshooting with a CGA card last time, although I don't really remember. But the fact is the computer starts to boot the rest of the way. So we know that that is not the problem. Oh, and look at that, that sticker, where's my marker? I can fix that now. So XT Turbo, this is not a turbo, by the way. People had pointed out that right here is what would be the turbo circuit, and it is not installed. There's room for an extra crystal and a couple extra components. There's probably a way for me to repopulate these and turn this thing back into a turbo, although not with this original 8088. This is only good for 4 megahertz, but with the right chip in there, and I don't know about this NEC clock generator, that might not need to be fixed as well, but I'm gonna say fixed. Wow, so Ollie, thank you very much for that tip. I am so glad to be able to definitively see how this chip had gone bad and the output driver was faulty. And I guess it's a cautionary tale that even when you use these logic testers, that sometimes it says a chip is good and it is not good. It really is gratifying to see the actual failure right there on the oscilloscope. So I would love to thank everyone who commented with suggestions on how to fix this, and especially to Ollie for really pointing me in the right direction. Thanks to all my patrons. Their names are swirling up the side of the screen. Thanks to all my viewers. Thank you to everyone. And I'm recording this right near the end of the year, end of 2021. So I just want to wish everyone a happy new year. And I'll see you all in the new year. Stay healthy, stay safe, stay healthy, stay safe, and I'll see you next time. Bye.